I have to print out the thing for him first. Wait, hang on. Tristan, you go and get it. You need sanitizer? This is pure alcohol. You want?
Oh, I thought it was like, because of the sun, it became like water.
No, it's pure. It's pure. You want pure? Oh, like what do you not want then? It's not. It's pure white. Pure clear sanitizer. E1. You have. Alright, you have. So it's just him. Is John Zane coming? Does he have E1? Ah, shoot. Oh, I may have printed him for him on Sunday. Go. Forgot where. He has to go all the way back to somewhere. He was refilling his water bottle. From what? The toilet? No, he walked out. He's gone. Oh, okay, that's fine. Okay, sorry, let's start. Yeah, I'm a bit delayed here already. Okay. So what do we do over the weekend for E1? No, not yet. Not exactly. Yeah. Yeah. So we're gonna go through all that now. So just a recap, we have gone through all these spectra, line spectra, emission spectra, absorption spectra. You got to remember like when you can get absorption, when you can get emission spectra. Okay. And then we've done some questions, and when we had this closest approach method, right? So B1 is very complicated. Sorry, not B1. E1 is very complicated because the first part of the chapter is what? About the atom, about the electron shell. Okay? The second part of it, right? The second part of this chapter, right, is about the nucleus, right? Which is very annoying because now you have to go and figure out what's the nucleus size, right? And then the very last part of this chapter is about the Bohr's model, which is back to the atom again, right? Which is again very frustrating, right? Yeah, but it's fine, okay? So technically speaking, maybe next year I will just make it such that the nucleus, right? I don't teach it in E1. I'll just teach it in E3 when we're doing decay. I don't know why they formatted the chapter like that. It's so annoying. Maybe I don't get it. I really don't get it. Okay. Can anyone tell me what's going on for this one here? Right, alpha particles with known Ke flying towards the atom, and then it kind of like U-turns just before it reaches the nucleus. Right? What's going on here? What's the concept that's happening here? Repulsion? Why is the alpha particle being repelled? So positively charged alpha particle is being repelled by the positively charged nucleus. Am I right? Okay, good. Right? Is he right? Yes, he is. All right. But how do we know what is the Ke that alpha particles have? Like it says alpha particles with known Ke. How do we control that? But how do we know how much Ke, or how do we control the amount of Ke that it has? Well, not quite. Velocity selector will help us figure out what speed they are, but it doesn't let us control the speed. How do I control the speed of an alpha particle? Potential difference thing, right? Parallel plate. So you use a parallel plate. Okay, you use parallel plates like this, right? And then you have an alpha particle, and then you fire the alpha particle, right, in between the two plates like this. Okay? Let me give you an example, right? Let's try an example. Let's say this is a 2000 volts, right? Negatively charged 2000 volts, right? Plate obviously has to be negatively charged. If not, it won't be able to attract the alpha particle, right? So once it flies through that hole, what is the Ke of this alpha particle? Right? Be very careful before you answer, yeah? What's the Ke of the alpha particle? Yeah, be very careful before you answer. 4,000 eV, why? Why 4,000? Right? Alright, so you got to remember that the alpha particle has 2 protons, so the charge of the alpha particles, the Q of the alpha particle is actually 2e. Right? So the Q, oh sorry, not 4,000 volts, 4,000 eV. Sorry about that. So 4,000 eV. Okay. Where does this equation come from? Like Ke equals to something times something. Where did the equation come from? What? Yeah. Okay, work done. Work done equals to Q del V. Correct. Okay. So that was from D2, right? Electric field. So Q del V. So the charge of the alpha particle multiplied by the volts, you get 4,000 eV. Now eV is what kind of units? It's a unit of what? It's energy, right? But it's not the SI unit. So you got to remember how to change it to joules, right? So I mean, most of you here, I mean, didn't you didn't attend the lessons from last year. So how do you convert EV to joules? Yeah, all right. So the conversion is 1.6, right? So 1 EV is equals to 1.6, right? Times 10 to the power minus 19 joules. I mean, just in case you know, EV means electron volt. Right, it's a unit, electron volt. Okay, so sometimes you do see. I mean, actually for this chapter, you see more of MeV. You see more of this unit here, MeV. What does that stand for? Mega electron volts. Okay, good. Right. So what's happening here? So the alpha particles with this amount of Ke is flying towards the nucleus. Right. It's being repelled, so U-turn. So can you tell me what's going on here in terms of energy? What's happening there? How much is the Ke over there? Yeah, the Ke there is 0, right? K equals to 0. Okay? K equals to 0. And then we are and what happened to the Ke? What does it become? EPE. Correct. EPE. Right, EPE. And what is the equation for EPE? Come on, give me the equation for EPE. KQQ over R. No square, yeah? KQQ over R. So KQQ over R. Alright. So just to remind you that what we're doing here is we're trying to equate the Ke into the EPE. So if we know the amount of Ke that we fired it with, right, we can equate it to the KQQ over R, and then we can use that to help us find like the amount of R. Like what's the R? What will R be then? Like what will R represent? Closest approach distance, right? So it's not written here, right? So yeah, so R is called the closest approach distance. Closest approach distance, right? Closest approach distance, right? That will be the R there. Now, what's the significance of having this closest approach distance? At the end of the day, what we're trying to do in this picture here, we're trying to estimate, right, the nuclear radius. So this would be a good approximation, but it's an approximation only, right? This is not the best method, right? So what's an even better method? I mean, this is the roughest. This is like the start, right? They imagine, okay, this is what we can do, right? And then, it led on to the next, into a more refined method. So what's the next method? Well, next page, what's the next one? What's the next one? What's this? Yeah, this is the Rutherford deviation, right? So it's the same thing essentially. So what he's doing is that he's just increasing the Ke of the alpha particle, and at that particular Ke here, it got so close, right? It got so close that the alpha particle touched the nucleus, right? That's what we said over the weekend. So the alpha particle, right, got so close that it touched the nucleus, right? I mean, since we're using lead, so it's a lead nucleus here like this, right? And what are the two outcomes of this Rutherford deviation, right? One more time. I mean, since we're doing revision, so one more time. What's the two inference that we can get from here? We infer that the strong force, right, acts on the alpha particle. When it got so close, it touched the lead nucleus surface, right? So there's the existence of a strong force, right? It's like a grappling force, right? I like to call the strong force the handcuff force. Right? In order to handcuff someone, you have to be that close. right? So if let's say I put on handcuff here and I want to handcuff myself to him, which is wrong, right? Then I have to be like that close. I cannot throw handcuffs, right? Okay, so strong force, right? Strong force will whoa. You have to see here. You not go school, ah? Ippon school. Why? You woke up late for school. Nice. Okay. Okay. So there's the existence of strong force. You get what I'm saying? Right. But oh, kena whack already. Wow. A delivery service some more. Okay. You woke up late for this class also. Ah. Then so after that, you also can use this idea, right? Because I know what's the initial KE of the alpha particle, I can also use this idea to figure out what is the distance of closest approach. This time round, we sort of know that it's so close that it touches the surface of the lead nucleus, right? It's so close that it touches the surface of the lead nucleus. Correct? That's how the strong force is effected, right? Okay? Which means that this R can be considered almost the radius of the nucleus already. Okay? So if you do use the same equation, KQQ over R, right? KQQ over R, the R here is pretty much almost the size of the nucleus, but not quite actually. Right? So in reality, this still not the best method. Yes? No, they won't ask you to compare the method, right? Like I repeat again one more time. So from E1 all the way to E5, and I say like E1, E2, E3 lah, okay? Right? You will get a lot of different kinds of experiments. You need to figure out what experiments are for. So if I give you a Rutherford deviation experiment, you need to just tell me what is it for. It is to help you compare, right? So help you find the radius and help you understand strong force. Okay? Can? All right. Now, just to be very, very clear, pass him the tissue. Just to be very, very clear, hey, don't give him one piece. You pass that one piece of tissue, everyone touch. The tissue is already very... Then I think he also don't dare to wipe. Everyone's hands on it. Hey, so what's this Q and Q? What's this Q and Q? Charge of lead and charge of the alpha particle. Right here, right now, tell me what's the charge of the alpha particle? So 2 times 1.6, right, times 10 to the power minus 19. And what's the charge of the lead particle? 82 times 1.6 times 10 to the power minus 19 coulombs, right? Anyone, any issues with wondering why it's 82? No, Okay. Okay, good. So, there we go. This will be it, right? In case we get this one. Okay, let's go on to the next one. Right. So the next one. Yeah, what? Okay, what? What do you want? So, oh, I heard proton. What was it? Oh, this one is the proton, number of protons inside the lead nucleus. So the charge of the lead nucleus is 82 times the proton charge. Yeah. Okay, can yeah. Charge, not mass, charge. Yeah. So, huh? You lost the last 2 pages of the notes. Your dog ate it. Hey, oh, there's a spare piece. There's a spare copy here. It does, yeah, it does. Okay. Take. Hey, I lost my train of thought. What? Oh, yeah. So the third method and the most accurate method is called the electron diffraction method. Electron diffraction method. Hey, how come you don't have the notes? Pass it back to him. Pass the stack to him. It's just missing the last 2 pages. Yeah. Huh? Yeah, I'm going through that last 2 pages, but not yet. I'm not there yet. So I'm on this page now. Okay. Right. This here is weird being in E1. Because to understand this electron diffraction, we need to understand that electron beam can behave like a wave, right? Which is in where? In E2. What wave is it called? Huh? What? Yeah, it's called matter wave. Right? Yeah. I thought you said NATO wave, right? So yeah. I heard that too. Right. Wave, right? Like a wave. Okay, like a wave. It can behave like a wave, right? And then it can do diffraction, right? It can do diffraction, right? And help you find the size of the nucleus. Okay, it can help you find the size of the nucleus. So if you have no idea what's going on, right, or why does it work like this, so you better draw this in. So the idea here is you have a beam of electrons. What's the another name for electron beam? In case they try to be funny, what's another name for electron beam? Anyone heard of it before? What's that? Cathode ray. Good, right? It's called a cathode ray. So the electron beam is also known as a cathode ray. Electron beam is a cathode ray. You heard that? Electron beam is a cathode ray, right? So if you have a beam of electrons and if it's traveling fast enough, it will behave like a wave. And then when it hits the nucleus, right, of your sample here, right, it hits the nucleus of your sample here, right, it's going to diffract, right? So then this electron will diffract around the edges like this. Okay? Right? So what kind of diffraction is this? It's called single optical diffraction. Good. Back in C3, we learned single slit diffraction, right? Back in, I don't know, C3, the start of C3, what's the definition of diffraction? When a wave passes through an aperture or encounters an obstacle, it will, what's diffraction? It will spread, right? It will spread, okay? So the idea here is that it doesn't spread through the obstacle, it spreads on the edges, around the edges there, right? So it was, sorry, maybe I shouldn't draw it like that. Maybe I should draw it like this. So the electron beam hits here, right? Then it spreads like that, okay? So then you get diffraction like this, right? So you get diffraction around the obstacle. You understand this? Single slit pattern. How does a single slit pattern look like? Right, just draw a single slit here. Right, how does a single slit pattern look like, guys? Yeah, maximum center, then very small, not very high, very, very small. So it's something like that. Okay, so that will be a single slit pattern. Okay, for single obstacle, right, we take it that the pattern looks very similar to single slit. So if your single slit is a little bit shaky, you better go and review your understanding of single slit. What's the most important 2 points on a single slit pattern? The central maxima and the first minima, right? The first minima. So what happens is that this electron diffraction around a nucleus, the pattern looks very similar to this single slit pattern. So it kind of like looks like that, right? Like this. Okay. So it looks like this part here, this one here. So usually they only show you like the half of it. They tell you that, oh, there's a detector that detects this thing here, right? So what this tells us is that the diffraction angle, right, being 35, right, right, is the angle to the first minima. You understand? So the single obstacle diffraction uses the same equation as your single slit diffraction, which is what? Okay, for single slit, right? But technically single slit, we use what? Theta equals to lambda over b, right? Okay, right? But it's okay to use sine theta. You understand that? Right? So sine theta equals to lambda over b. It's actually okay to do that. Right? So for here, we use sine theta equals to lambda over d. We use sine theta equal to lambda over d. Why? Because, I mean, b is for what? Slit width, good, right? It's for the size of the slit. But we are not passing through a slit, we're passing around the obstacle now. Right? So this d here is the diameter of your nucleus. This is the diameter of your nucleus. Okay? All right. So what we're gonna do is we're gonna use this, right? We're gonna use this sort of equations here to help us calculate something, right? I made a mistake for one of these for the values here. I just kind of like threw in a random value. So technically speaking, I actually don't know what's the K of the electrons, right? But I'm going to use this one here, this 35 degrees. Okay, so you see this more accurately, 1.22 lambda over b. Okay, cancel this out. Right, just cancel this out. Right, for real, because this one already. Okay, you cannot. Right, so she's got a question. Can we approximate beta equals lambda over d? The answer is no, because this angle here, 35, is 35 degrees. Right, it's 35 degrees. Right, which means that this angle is no longer small. You cannot do small angle approximation. Okay, I think what we're gonna do now is this. I'm gonna tell you. I'm gonna work it the other way around. I'm gonna tell you that. Give me an approximate size of a nucleus. Can you tell me like what's a what's a reasonable size of a nucleus? Like just give me a value. 3 times 10 to the power minus 15. Good. Right, that will be a good estimate. We're gonna use that now. Given that the size of the nucleus is 3 times 10 to the power minus 15 meters, given that the first minimum angle of this electron diffraction is 35 degrees, right? I want you to back calculate, find the Ke of the electrons. Yeah. Like how fast was the electrons? How much Ke does the electrons have? Yeah, we're gonna work backwards now. Okay? Alright. So first things first, we use sine theta equals to lambda over d. Right? I mean I gave you the d already. Right? I give you this 35 degrees already. So sine in degree mode on your calculator, sine 35 degrees, right, equals to lambda of my electron beam. So this is the lambda of my electron beam, right, over the size of that nucleus, right, 3 times 10 to the power minus 15, right. Notice how I agreed with his value. It's not some random value that he chose, right? Because 10 to the power minus 15 is the typical size of a nucleus. So anything like 3, 4, 5, is okay. All right. So then what we do now is we go and find out what's the wavelength, right? What's the stated wavelength of the electron, right? Yeah. It means yeah, it's short.
Wait, I got 8.1480 times 10 to the power minus 8 or 5K.
No, I'm trying to find the wavelength first. What?
Wavelength
Times 10 to the power minus 15 meters. Okay, 5 minus 15 meters. We're going to use this and go and find out what's the momentum of the electron, right? So what's the momentum of the electron? So wait, 6.63, right? Times 10 to the power minus 34 over 1.721 times 10 to the power minus 15. Hey, sorry, what? No, over P. Sorry, over P. Oh, sorry. So this is P here. No, so it's over lambda. What's wrong with me? Over 1.721 times 10 to the power of minus 15, and that's P, right? And therefore P is how much? 3.85 times 10 to the power of minus 19, right? And then Ke equals to P squared over 2m. K equals to P squared over 2m. Okay, so we have that one. So 3.85 times 10 to the power minus 19 squared over 2 times 9.11 times 10 to the power minus 31. Right? Yeah. 8.15 lah. Times 10 to the power of minus 8 joules, but I want it in mega electron volts. Yeah, give it to me in mega electron volts. What?
That's a bit big for you.
That's a bit big.
Yeah.
What went wrong? So it's in giga lah. That means it's in giga. So if I put giga electron volts, 509 giga electron volts. Hmm. Times 10.9. Yes.
What do you use like the restaurant when you
No. Okay. That was the same question as just now. No, but what do you mean by rest mass? What rest mass of what? Ah. Uh-huh.
because the question is about the energy, right? They all use atomic mass.
Okay, hang on. When we talk about binding energy, is with regards to the which part of the atom? No, which part of the atom? No, the nucleus. The nucleus, right? Got nothing to do with the electron. Correct. But your question is actually asking rest mass of proton and neutron. Okay, hang on. Hey, the rest of you, do you get this number? You all got this number? 509 giga electron volts. This one, that's the mass of electron. Mass of electron, yeah. Hey, don't just be calculating. Make sure you write down all the workings. I will address your question in just a while because it was the same question that the SL class had as well. So I think I better make sure that we clarify that issue. We good? Clean one there. No, don't write down. Finish writing? Can? I do, Okay, I go on, Okay. Now, with regards to the nucleus, right? With regards to the nucleus, I again have this question, so I better address it now, right? This has happened yesterday. This has happened today for SL. So I'm just gonna, intervene now and tell you this, Okay, what is this? Unified atomic mass unit. Actually, why got unified? Got unified, man? The word unified is inside. Okay. I just call it atomic mass unit. Right. So it's a atomic mass unit. All right. Maybe that's why. Maybe it's a good reason to remember that it's unified. What's the definition of this? 1U represents what? 1/12 of carbon 12 atom, right? That means you take a carbon atom, you cut into 12 parts, right? That's the mass, right? Okay. What's the layman's understanding of 1U? Mass of? Okay, it's the average mass of a nucleon in a nucleus. Can you write that down? 1U is the average, right? Average mass of a nucleon in a nucleus. Like, wow, big words. What the heck does that mean? It means that what's a nucleon in a nucleus? What's that? There's proton and neutrons only, right? So nucleon and nucleus is either only protons or neutrons, right? There's no other things, right? It's either proton or neutron. Okay? So the idea here is, right, either the proton or the neutron in the nucleus has an average mass of 1U. We just take it as 1U. So let's say I ask you, what's the mass of a helium-4 nucleus? What's the mass? Mass of helium-4 helium-4 nucleus, right, will be equals to what? 4U, 4U. So you take 4U, right? But hang on. A helium-4 nucleus is made up of how many protons, how many neutrons? 2 protons, 2 neutrons, right? Okay, stop, Right. Can you tell me what's the mass of 1 proton in terms of U? In terms of U, like how much is one proton mass? 1.007276 U. And then how about 1 neutron then? What's the mass of 1 neutron? 1.008665 U. Okay? So you need to understand that the individual masses of protons and neutrons are actually higher than the average mass of the same nucleon in a nucleus. So the idea here is that when you form the nucleus, the protons and neutrons lose weight.
Okay.
Right? Yeah, the cutting off the the liposuction thing, right? So they lose a little bit of mass, and therefore on average, right, all protons and neutrons inside the nucleus would have 1 U worth of mass, right? So yeah. So if I ask you what's the mass of helium-4, and you go and take 2 individual protons and 2 individual neutrons, you add it up and you say that that's the mass, right? Okay? It's not right. I wish I can tell you that. I can agree with you. I just did the paper with the SL students, May time zone 2, paper 2. Alright? They're supposed to take 4U as a mass.
Shit, really?
Yeah. However, so one of them, the teacher went through that question, told the student it's okay to take 2 protons and 2 neutrons. Okay? Mark's scheme also says it's okay to take 2 protons and 2. No, cannot. Because that destroys your understanding. Right? If you're trying to find the mass of a nucleus, already formed nucleus, you got to use U. Right? You got to use 4U. If you're trying to find the mass of individual protons and neutrons, go ahead, use this one. What? Yeah. Is it a nucleus already? Is it formed already into a nucleus? Are we talking about an actual? No. As in, are we talking about an actual formed nucleus already?
Yeah.
It is. Then you use 4 times U. So what is this? This is the individual protons and neutrons that haven't been forced into a nucleus yet, haven't been combined yet. So you got a whole bunch of like 1 proton, another proton, and neutron here like this, right? Right. You got like 4 scattered particles, and then by some process we can squeeze them into proton, proton, neutron, neutron, like this, right? So the mass will be different. These are 2 times this plus 2 times that. This one here is 4 times the U for this one here. So unified atomic mass, right, is just the average mass, but you cannot write that down in an exam. In the exam, you cannot say that, oh, it's the average mass of a nucleon in the nucleus. Although it really just means that. Right? The proper definition of it is 1/12 of a carbon-12 atom, right? So blah, 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 blah. But they will never ask you that anyway. Right? You just need to remember this. You just need to remember that you use U when you're dealing with nucleus. Yeah, nucleus. No, what fission? When you use a neutron to the uranium-235, that neutron, yeah, that's a stationary. That's a standalone neutron, right? And then you use this one, yeah, it's fine. You don't use 1U for that. Yeah, you use the mass of a neutron. Okay, yeah, and electron don't come into play,
Yes.
Electron doesn't come into play. So technically speaking, when you do binding energy, we're only dealing with the nucleon. So 2 protons, 2 neutrons, right, form a nucleus, right? The mass is less, there's mass defect, there's energy released. Okay, sure. But mass defect from adding on electrons. Right? But we don't do that, not in our syllabus. Our syllabus, we don't add on the electrons. If you had to, you had to. Like, how many electrons do you have to add to it to make a... You had to add 2 electrons, right? To make a helium atom, right? Yeah. But that's way, way, way too small. The mass of the electron in itself is already 10 times 10 to the power minus 31. So the mass defect from adding 2 electrons is minuscule. So we don't really care about this mass defect due to adding of electrons. Most of the time, right, until, right, sorry, which is, yeah, most of the time until you have atoms that have like 92 protons and 92 electrons. Then that becomes a bit substantial. But otherwise, we don't care about it. Okay? And about electrons. We don't care about electrons. Okay. So are we all clear on the very accurate method of finding the nuclear radius? Or nuclear diameter, sorry. So this equation helps you find the diameter of the nucleus, okay? Right, the diameter of the nucleus, yes? Oh, yeah. Can. And then we come to this equation here. Right, this equation. Oh, Jace, yes? What's up? Jace? You raised your hand. Oh, accident. Okay. Right. Okay. Hang on. All right. So, all in all, right, after you have dealt with all the different methods of finding the nuclear radius, you have to come down to this equation, right? You have to know this equation. What does this equation do for you? Find the radius of a nucleus just simply based on what? Huh? Just simply based on mass number, right? Mass number, not atomic number. Mass number. Atomic number is smaller. What's atomic number? You all take chemistry on, right? Huh? This is not atomic number. This is mass number. Yeah lah. What does atomic number stand for? Proton number. Atomic number is proton number. Mass number is what? Total proton and neutron number in the nucleus. Okay? Hey. What? Why does A not stand for atomic number, is it? Because it doesn't. Not my fault. Yeah, it's damn annoying, right? Yeah, freaking hell, why can't you just put like ZA or something like that? Atomic number at the bottom, can what, right? What's R naught? Fermi's radius, okay? Fermi radius, okay. So, alright, so this one here, I don't have to go through that much, right? Unless they ask you to go and estimate the size of nuclei, right? Like, given a difference, right, in the size of nuclei. Let's say, for example, I ask you, what's the ratio of nuclear size, right? Nuclear size, right? Between uranium-235 and helium-4. Yeah, what's the ratio of the nuclear size between uranium-235 and helium-4? Like, what's the difference in their size? 235 over 4 to the power 1/3, right? Yeah, there you go lah. So the difference, the ratio of their size is 235 over 4, right, to the power 1/3, which is how much?
3.89.
3.89. 3.89. Oh, okay, that's not much actually. Oh wow, that's actually not much. That's like what, 4? Really? 4 times only? Oh damn. Okay, that's really not much then. Okay, that's surprising. That's so many more neutrons. That means you really pack in a lot more, right? Okay. Anyway, all right. What's another application of this equation? Like, oh, I'm going all over the place. Hmm.
Wait, hold on. Sorry.
We are. Yeah. So the other use of this equation is to find what? You say find density. What density? Nuclear density, guys. Nuclear density. All right. We'll find it in a while. Sorry, what's the question?
So yeah, okay, about the unified atomic mass is about the same for just now it says about the same for every atom. Is it because of this has the same extremely high density?
Yeah.
So because the volume
Yep. Okay. How about nuclear density? How do we find nuclear density, guys? Ayo. I think I better find some space here. Okay. Nuclear density. Right, nuclear density. How do we find nuclear density? Mass over volume lah. Mass over volume, right? I just said it. How do you find the mass of nucleus? Mass of nucleus over volume of nucleus. All right. So how do we find? Yeah. A times U. Right? Then divided by, what's the volume? 4/3 pi r cubed. But we know that r is equals to r naught a to the power 1/3. So it kind of like very conveniently, a will disappear. Right? So 4/3 pi r naught cube a. So a will cancel off. Right? Which means what? It's basically one atomic mass unit divided by 4/3 pi Fermi's radius cube. All right. Work it out. Yeah. Work this out. For real. Like I want a number. Doesn't matter. Because this is the density for all of the nuclei. Yeah. Atomic mass unit is a constant. Fermi's radius is a constant. This thing is a constant value. All nuclei have the same nuclear density. Who keeps pinging me? Someone keeps pinging me. Say what? Sounds about right. 2.3 times 10 to the power 17 kg per meter cube. Right? That's dense. Okay? That's hella dense. It's really very dense. Okay? So do you understand that if I ask you, what's the density of a helium nucleus to a uranium nucleus? It's the same, right? It's the same. It's 1:1 ratio, right? But if I ask you, what's the density of helium compared to uranium? Do you understand that's different? Helium is a gas. Uranium is a solid. So if the nuclear density is the same, how come their overall density is not the same? What's the overall density got to do with it? Like, what is it affected by? Huh? No lah. Come on, guys. Okay, helium is a gas. Uranium is a solid-ish. Right? So helium has low density. Uranium has high density. But then the density of the nucleus is the same. Why? The what? Atoms. So the density of the gas and the solid depends on the space between the atoms. Right? But if I'm asking you for the density of the nucleus, it's the same. Yeah, they might ask you, but it's a very weird thing to calculate. Yeah. But it's not about the density of the atom, right? So the density of the material depends on how far the particles are from each other. So it's like you could have a helium particle like this, right? And another helium monoatomic, right? Helium like this, right? It's a gas because, they are very far away from each other, right? And then yet for uranium is tightly packed. So uranium is a solid, okay? It's a solid. But here's the thing, the nuclei, this nucleus and this nucleus have the same density. You understand what's going on here? What's the difference I'm making here? Okay, All right, there you go. So that's about nuclear density. Which incidentally, you have to know for what does this density also represent? Those who attended this before, what does it represent? This density. What's this density also equals to? Something from E5. What's that? It's the density of a neutron star. This is the density of a neutron star. Right? This is the density of a neutron star. You might be wondering, do I need to know this? Yeah, sort of. Okay, you sort of need to know this, so I'm going to go down the rabbit hole for this one, for the neutron star, as I did with the previous class. Okay? What was this? Oh, okay, All right. So you gotta remember the evolution of stars. Evolution of stars, okay? You gotta remember that. Okay, low mass stars. Low mass stars. Alright. I'm not gonna quote numbers because we can go through that later on. Right? But for now, the general idea, low mass stars, right? What happens to them? Like, eventually, what do they become? Red giants, and then what do they become? White dwarfs, right? So white dwarfs, okay, and that's it, end of life. How about high, what? Black dwarfs? Yeah, well, black dwarfs are just white dwarfs that emitted all their light. Yeah, they totally cooled down already. So high mass stars, right? High mass stars, what will happen to them? So they become super red giants first, right? Super reds, right? And then after that they will supernova, and then they could have two pathways. So it either becomes a neutron star, or a black hole. Yes. Right, don't worry, this part here died already. No, this part here also died already. Yeah. Don't worry. Yes, of course. Yeah, I mean, that one later on. I think no, they matter. They also matter, right? So what we want to do is we want to focus on this one here. I want to talk about this one, the neutron star. What makes a neutron star a neutron star? Okay, what does a neutron star mean? What is it made of? It's made of completely neutrons. That means you have a core that's completely made of neutrons. But why? Why is it made of neutrons? Why is it completely made of neutrons? So you gotta understand the structure of the atom. The atom is made of a nucleus, right? You got your nucleus here, right? So imagine this is like proton and then proton here like this, and then you have your electron. Now the gravity of surrounding particles is so strong, it's so much that what happens to that looks like the word poop. But okay. Whoops. What happens to this thing here then? Okay. It gets whoops, sorry. Oh yeah, that's right. Okay, you all understand that. Wait, how come you all understand that? Huh? I said it before. Okay, you all understand that. Okay. No, cause yesterday's class was like, what's that? I was like, huh? What do you mean by what's that? I said it before. Okay, so the gravity is so strong that the electrons are basically, this is a very rough idea of it, right? So it's being crushed inwards. Oh, why is there another one? Okay, so it's being crushed inwards like this. It's being crushed inwards into the poop, right? Like this. Okay, crush, like that. Okay, right. So now the electrons are all crushed inwards, and what happens to the electron when it touches when it's being crushed into a proton? It becomes a neutron. So the electron will add on to a proton and becomes a neutron. Okay? So what you're left with in a neutron star is such a high gravity that all the atoms are all being crushed. It has gone past what we call the electron degeneracy pressure. Right? Right. Gravity is stronger, right? And gone past the electron degeneracy pressure. Okay, electron degeneracy pressure, right? And therefore, it becomes one whole big ball of neutrons. No charge. Super dense. Right? Density is 2.3 times 10 to the power 17 kg per meter cube. Okay? Right? And that's what makes it a neutron star, because of the super high gravity. Sorry, what? Yeah, correct. That's right. Yeah, it is right. Could you crush it even further? So if you had pure neutrons, right? If you had like a whole ball of pure neutrons, and you crush it even further with gravity, right? It means the gravity's strength is so strong that you've gone past the neutron degeneracy pressure, right? The neutron degen pressure. Right? So if you manage to crush past the neutron degeneracy pressure, it will become a black hole. Yeah. So it'll become a black hole. Yeah. Huh? What? Right? Nobody knows what a black hole is really made of. Right? So yeah. I mean, there's some theories on it, but yeah. The idea is just swimming with subatomic particles and all. I have no idea. Mm.
If you can see what is, if you can see a black hole, what's the chance of you dying? Because I've heard before that the moment you can see a black hole, you're probably going to die. Yeah. It's a very
Yeah. I don't know about the kind of questions, but there's more like a like hypothetical for fun kind of question. All right. Toilet break. Toilet break. Snack break. Do we have snacks around? Oh, the May paper. Yeah. Yeah. Did someone ask for Mars bars the other day? Did anybody ask for Mars bars? No. It's not a Snickers. Okay. What's going on? Hmm? I don't know how to answer that question. Okay, let's go.
Don't go around saying that.
Yeah.
Doesn't exist in the
Now talk about free speech, then you have to pay the price. Okay, let's go on and do this one. So we need to talk about Bohr's model now. Bohr's model. Yeah. So what did Bohr do to create his model? What? He made up equations. Okay. He's not wrong. What is his assumptions? What is his model based on? What's the electron doing? Huh? No. Okay. So what do we okay, I think the first thing is to understand firstly that Bohr's model was derived from the fact that he treated the electron like a particle. You understand this? Okay, he treated the electron like a particle. And what is this electron doing? What's it doing? Orbiting around the nucleus. So am I right to say that this electron acts like a satellite? This electron is acting like a satellite. It's orbiting. What kind of force is it using to orbit? I mean, centripetal force, but what type of force really? Electrostatic force, right? So there's this force that it's experiencing, and it's using this force to act as a centripetal force. So it's like this is the Earth, this is the Moon, right? Satellite. Same idea. You get what I'm saying? Okay. What's the equation for that? What's the electric force? What? KQQ over R squared. KQQ, Q1, Q2 over r squared, right? That will be the force, right? That's acting on the electron, right? And this force is providing for the centripetal force of the electron. Okay, and therefore this electron will orbit around this thing here. Okay, what was one of the observations, or rather, what's one of the inference with regards to energy about the electron? What's that? What doesn't lose energy? The electron doesn't lose energy, right? Is that possible that the electron doesn't lose energy? Yeah, it is possible, right? What happens if the moon loses energy? Yeah, it will crash in on the earth, right? So this electron doesn't lose energy, and therefore what does the electron do? It continues to orbit around the nucleus. Okay? What's the proof of that? I mean, he inferred that the electron doesn't lose energy, right? But what's the proof? The fact that you exist. The fact that everything around us exists in the first place means that the electron is not colliding into not crashing in or collapsing into the nucleus. You get what I'm saying? No?
Is that seriously?
What happens when? Yeah.
Wait, what really?
What do you like?
If they ask,
Like, what was one of Bohr's assumption is that the electron doesn't crash in the nucleus. Why? Because it doesn't lose energy. Because if it did, what happens? Everything becomes a neutron. Right? No, I'm just saying that the electron doesn't lose energy, right? The very fact that everything around us exists is because this electron doesn't crash into the nucleus.
It's a snake deal.
So Bohr's model, so if you go and read the history of Bohr's, like, creating his model and all that, I think Veritasium just posted it not too long ago, a couple of posts ago. Bohr almost didn't want to release his findings. Like, he did all these things and he almost didn't want to publish it. You know why? Shy. No, really. You know why was he shy or not? Because he realized that his whole entire model, right, only works for hydrogen only. So he a bit paiseh. Shit lah, walao. How come I do all this work, right, actually only work for hydrogen? Then you know who encouraged him to continue? Rutherford. Rutherford said, no lah, go and publish lah. Right? So you lose 100% of the chances that you don't try, is it, or something like that? So he went ahead and tried it, and he got the Nobel Prize for it. He got Nobel Prize for this, right? Yeah. How does what help? No, so there's like, the idea was very close. He almost could model the atom by using just purely math. So it makes sense, right? Okay. What's the big deal with Bohr's? Like, what's the big picture with Bohr's model? Bohr's model tells us that the particle model of the electron works. The particle model makes sense. If you treat it like a particle, you do all the equations, you do all the math, it makes sense. You understand this? Yeah, I mean, it's only for hydrogen, because when you have more electrons, what happens? Guys, those who take chem, what happens when you have more electrons? What's the other effects? Shielding effect. Right? You got all the other different effects, right? So you don't have to know that. But the idea here is that his model only works for a single electron because of the absence of other electrons. You get this? So what happens is that Bohr's model can actually be used for hydrogen, for single ionized helium, and double ionized lithium. All of which means what? Only one electron. Only one electron. So Bohr's model work for single electron models, which I think at most you only can have like 3 different versions. Huh? What are you talking about? It's just spectrum from nowhere. Huh? What? No, okay, no, that. Yeah, I know, but the connection is not. I don't see the connection. You are not getting the right connection. Absorption emission spectra is for all kinds of atoms, any kind of atoms in the entire universe, entire periodic table. You can get the emission and absorption spectra for any kind. But Bohr's model, his equations here, can only be used for hydrogen, and maybe these other 2 things. the other two things there. Single ionized helium and double ionized lithium, maybe. Right? So his model is not a universal model. It cannot be applied to all the other atoms. You get it? So it's not the same thing as what spectra. Right? I know you see the energy levels there. Right? But what happens is that Bohr's equation, this equation, is used to calculate the energy levels of hydrogen only. Okay? It is not written in your data booklet, but you have to remember that this equation is for the hydrogen's energy levels. And only hydrogen, not some random atom. You want to ask a question, what do you want to ask?
I'm missing 2 pages.
You want to return the 2 pages to him? Okay. Right, 15, 16. Right, just print out 15, 16. Hey, Melpan, help me collect and pass to him. Poor Nidish. Only gets like half the notes. Okay. Now you don't have to do the derivation. I swear to God, if it come out derivation, I'll flip table. So you don't have to derive any of this nonsense, but there's a few parts that you need to memorize. Okay, you need to remember. Like for example, this equation here. What's up with this? What's this thing here?
What's FC?
So what's Ke squared? What is okay? So this is not kinetic energy squared. This is K, as in Coulomb's constant, K times E squared over R squared. Okay, it's not Ke squared. All right. But yeah, why is it E squared? Why is that E and E? One proton, one electron. One proton, one electron. So it's just basically the electron is attracted by the proton. So E times E squared. mv squared over r is the centripetal force. So you know what Bohr did was basically, in a very simplified version, of course, right? He just did the equation, and since it's orbiting, right? Since the electron is orbiting, right? Then we can consider orbital energies. Orbital energies. Orbital energy, anyone? D1 gravitational fields. Orbital energies. When I say D1 orbital energies of gravitational fields, what are you supposed to recall? What's the first thing you think of? No. What? No. I want orbital energies. What do you think of? The graph. The graph. What graph? What graph? Yeah. So whenever the next time you see this thing, orbital energies, right? Orbital energies, right? Always remember this graph. Right? So if you're like, oh, I've never really seen this graph before, right? You know what to do, right? You have to go and revise this graph here. What's the top energy? What's the top one? Ke. Bottom is Te, and most bottom is GPE, right? GPE for gravitation, but for this chapter, the most bottom one will be EPE, right? The most bottom will be EPE. There we go. Right, this will be EPE. Are we aware of that? Can the electron is orbiting, so we consider the orbital energies. So you can find the EPE of the electron, you can find the K of the electron, you can also find the total energy of the electron, which is given as this equation there. Look at the equation. Right? It's the same, right? It's the same format, right? It's the same format as the GPE equation. Sorry, the gravitational total energy. Why is it negative? Why is the total energy of the electron negative, guys? What? Why is the electron's energy negative, guys? Correct. It's still bound to the gravitational. You're remembering all the things I said. That's good. All right. So the electron has a negative energy. The total energy of the electron is negative because it's still bound within the electric field of the nucleus. It's still being attracted by the nucleus. So it goes around the nucleus. It doesn't fly off.
Oh, if it's 0, it's to infinity, right?
No, if it's 0, it crashed in. Oh, zero, sorry, zero total energy. Yeah, zero total. That means it has maximum energy. That means it's ionized,
It's first right.
Okay.
right? To ionize something means to kick the electron out. Yeah. Then you get a H plus. You get a proton. Okay. So these are the important things that Bohr did. Bohr treated the electron like a particle, and he did all these equations behaving like a orbiting satellite. Okay. So what's the other thing he did? Wow, some people are really angry on the streets, huh? Down here. This is that weird thing that he did. What does the equation represent? That's angular momentum. That's something from A4. Right? MVR is angular momentum. So L is equal to MVR, right? Equals to NH over 2 pi. Okay? So what does this tell us? This tells us that the electrons angular momentum, right, at different energy levels, at different ends, right, will be quantized will be an integer multiple of h over 2 pi. That's what quantized means. Quantized means an integer multiple of a base value. Okay? Right? What was the problem with this? Yeah, there's no theoretical justification for this. There is no, right? So he just assumed it, and then he fitted it into the calculations. He did the derivation, and then it just works.
What do you mean it just worked? Me, it got this coincidence.
Yeah. That's why
What?
shy also, right?
Okay.
Like what? Yes.
But you need to know the
No need. You see this red arrow here? Don't bother. But what you need to do, what you need to know is this part here and this part here. You need to know these two parts, at least. Okay? Because you need to know what were the stuff that he was considering when he came up to this. Okay? So yes, there's no theoretical justification for this angular momentum. Nobody knows why, or nobody knows how, right? But it's just kind of like you're swinging a pendulum, like, you know, further and further out, right? So the angular momentum, he just assumed that it will be quantized to this value here. Okay, and in doing so, when he did this, he did the derivation. It turns out that the total energy of the electron is negative 13.6 over n squared eV. Right? You understand this, huh? Okay? All right. What are you supposed to do with this equation? Yeah. So there was a question before in the IB physics, right? It's just straightforward, very simple, right? It was just like that. Photon, right? Photon was emitted from hydrogen atom, right? Going from n equals to 4 to n equals to 2, right? Find the wavelength. Like that. That was that question, 3 marks. Yeah. So one of the first things you need to notice was that they asked for hydrogen. So since they asked for hydrogen, you can use Bohr's model, right? So the idea here is that you have an electron on level 4, and then it de-excites to level 2, right? It goes from 4 to 2, and you need to find out what is the photon that was emitted. You have to find out the wavelength of the photon that was emitted from this transition. Okay? So, do it now. All right, let's do this. Russell, do you put your hands up? Sorry, what? Imply when a hydrogen atom is ionized, the energy required to ionize it is undefined. What do you mean by that? No, it's defined. What is n equals to 1? What's the energy level here? How much? Negative 13.6 eV, right? Russell? So how much energy do you need to give the electron if it was here to ionize it, to let it jump to infinity? 13.6 eV. Right? You make the total energy 0, the electron will escape. Okay, huh? Okay. So how do we use these two energy levels, and how do we find out what's the wavelength that's being emitted there? Yeah, so we need to find del E. Del E is equals to 13.6 over 4 squared minus 13.6 over 2 squared. Oh, the other way around, sorry. Yeah, the other way around. Oh, yeah. 4 squared is smaller, right? So you get a bigger number. I mean, whatever it is, it will just be the difference between these two levels, okay? So how much is this? 2.55. Please remember that this equation gives you EV. So now you need to convert this EV back to joules, right? You need to convert it into joules. You need to do HC over lambda. Yeah, you need to do HC over lambda. Times 10 to the power minus 19. And then HC over lambda is equals to that value. So 4.08 times 10 to the power minus 19. And then you use that to find lambda. 4.88 times 10 to the power minus 7 meters. This is 488 nanometers. Right, 488 nanometers. Right, 488 nanometers. Okay, 488 nanometers. What does it mean? What color is it? What? Who said that? What? What did you just say? Did you say purple? Your Roy G beef got P inside. No, right? Indigo, violet. Okay, but not really violet. Violet is more closer to 400, right? So 488 is about like either blue, right? Maybe blue, maybe indigo. Okay, right? No purple, Purple is a mix of red and blue. No, so in the before 2016 there was an IB question where they said that the question the experiment was they diffracted purple light. Students are supposed to understand that when you diffract purple light you get red and blue. Yeah, that's absolutely not fair. It's a crazy ass question. Yeah. No, ain't no way. It was a weird ass question. Okay. All right. Are we okay with this Bohr's model at this point? Yeah. So take note of these two equations and take note how to use this one. This equation there, and we are done with Bohr's model. All right. Okay, hang on. So a bit of a side quest, something for you to think about because it was taken out of your syllabus, right? But it's quite interesting. What did Bohr do to the electron again? He treated it as a. What happens if we treat it as a wave? What happens if you take your electron, right, around nucleus, right, and you treat it as a wave? Yeah. Specifically, what sort of wave should it behave like? Why should it behave like a standing wave? There's no energy loss, right? So a standing wave that exists around the circle here like this. You understand? And that's what Schrodinger did. Schrodinger. All right. Yeah, he is. Okay. So Schrodinger created an entire different set of models where he treated the electron like a standing wave, right? Which then gave rise to all your SPDF models. So his idea of a standing wave, right, is used to calculate the probability of finding an electron, and therefore you have all your SPDF models. Let's say, for example, 1s. What's the shape of a 1s? What's the shape of 1s? Like, it's spherical, right? It's spherical. How many electrons are there total? 2 electrons in total in the spherical shape, right? Okay. So what's an electron cloud? There's only 2 electrons, right? How can it be electron cloud? There's not a cloud of electrons, right? What is it? So the cloud represents the probability of finding the electron at that position inside the cloud. So an electron cloud is a series of positions where the electron can be found, right? The likelihood of it. Which also means that you can't possibly likely find the electron of a 1s electron outside of the 1s orbital. Unlikely, but not zero. That's another day for another time. Okay? But whatever it is, all these orbitals are all created by Schrödinger. So I'm a bit upset that they took it out of your syllabus because now you can't make the connection between the two. But now you know. Too bad. Okay. Alright, so I'm done with this. And let's go on to the paper. Let's go back to the paper because I don't have much time left. Right, I need to try to do as many questions as I can. May 25, time zone 2, paper 1. Not done yet, okay? Let's do that.
Wait, C is hard.
What?
C?
C?
Time zone C.
Time zone C is hard, okay. Yeah, good. Good. Yeah. No, hard is good. Y'all don't believe me. Hard is good. If it's easy, right, then you all end up, the grid boundary all 72, 73%. So I tell you already, last time there was 1 year where the grid boundary just suddenly jumped up to 72%. Then all the people who got 70, 71 all kena, all never get their 7s. Yeah.
Wait, so for each time zone they have their own grid.
Which is about the same actually end up. Statistically it's end up being the same. Let's start. 57. Yeah. Okay. Okay. Come on. Tell me which ones you want me to go through. What's that? Oh, we finished 16. Hang on, let me just double check where did I stop at for my Monday's class. I need to figure out where I stopped at for Monday's class. Monday is what date? Monday was what? 29. 29. Eh? No, Monday class. Tuesday class. My gosh. She's right. Tuesday class. Tuesday's class means what? Oh, 30th. Yes, yesterday only. Oh, yo, my brain.
Oh, frequency, yeah.
Oh, looks like I only finished up the MCQ only. Don't have enough time. Yeah, it's okay. Let's go. I stopped at 16, so I continue with.
We stopped at 22.
Oh, I mean maybe different Saturday, Sunday stopped at different place. Come on. No more already? What? 29, those are online as well. Come on. Right. Those are online. What? 24, 25, 19, 28, 29. Okay. Alright, I better type it down. One more time. 19, 24, 25. Anyone? 25? No, 26. What else? 28, 35, 36. Okay, so, right, this one here. Alright, let's go. 19 first, 19. 19. What? Hey, who's asking for this? 19. 19, hey, 19. 19. Okay, 19. Both ends closed. Right? Both ends closed. Hang on, both ends closed. How does a harmonic look like then? What's the significance of having both ends closed? So what? Both ends closed means what? What? Notes. That's right. Notes at both. Right. So how does a fifth harmonic look like? What's that? 5 peaks. So up peak and down peak is also considered peak, right? Okay, can. Right, so you got to understand that it's basically 5 halves. 5 halves. So 1, 2, 3, 4. Okay, I ran out of space. 5. Oops. Right, so you get the idea. Let me just try that again. So wait, or 2.5 lah. 1, 2.5. Right, like this. Yeah. Right. If you're trying to show standing waves, please draw the dotted lines. Right, there we go. Yeah. 2.5. 5. Yeah. So they did say that the length of the pipe is 25 cm, and you get 2.5 waves, right? So then they ask you what 2 points along the pipe have a phase difference of pi radians? Have a phase difference of pi. So for standing waves, right? What kind of phase difference do we have? How many versions of phase difference do we have for standing waves? Come on. Huh? Only 2 kinds, right? It's either pi radians or 0. Right? For standing waves, the phase difference of particles, there's only 2 kinds. Right? Either pi radians or 0. You know why? You don't understand why? If let's say you have 2 particles on the same section between 2 nodes, what kind of phase difference do they have? 0. If let's say it's one on this side and then another one on this side, then it's pi, right? So your job here is to find out what's the length of half a wavelength. Half lambda is how much? 5 cm, is it? 5 cm? Okay. So if you have, right, particles, right, within 5 cm, right, within 5 cm they will be in phase. Right? If they are beyond 5 cm, actually no lah. So you don't have to compare it like that, right? So basically, I think essentially, that means, you know what? It means you need to find out at every node, right? What's the distance there? Like what's the distance here? Like, and then the distance here, and then the distance here, and then the distance here, like this. And then you see which one is in the wrong section. Yeah. That means we don't do this. Yeah, okay lah. Then tell me lah, what? 5, 10, 15, 20, 25, is it? 5, 10, 15, 20, and then 25 mark here, right? So you see which 2 particles are in between the sections? 2 and 7 lah. First one lah. Like that's it lor. Right? Because 2 will be before 5, 7 will be after 5. Right? Then phase difference really, right? How about like 4 and 21? 4 cm and 21. Oh, okay, these people ain't playing. So 4 is here. 4 is here. 21 is here. Same phase. 0. 7 and 9. 7 and 9 both between the 5 and 10, right? Same phase. 11, 14. 11, 14 also same thing, right? Between the 2. Also same phase. So only A is the answer. Alright, that's for 19. The other class didn't ask for about this. I don't know whether they understand. Okay. Next one is what? 24? Do I do 24? Yeah, 24? Okay, good. So pair of parallel conducting plates are separated by 50 cm. One is 200, and the other one is 450. Proton travels from 200 to 450. Hey? How does that work? Okay, you see, I'm a bit confused about this because one plate is what? Is 450. Right? And then the other plate is 200. And then you have an electron. Sorry, not electron, sorry. You have a proton. A proton travels from the 200 plate to the 450 plate. How does that work? How is it possible? Is it possible? That means you must have given it energy at first. Correct. Huh? Wait, hang on. No, hang on. So that means you have to give it energy at first. That means it can start flying upwards. But as it's flying upwards, what happens to the energy? You must give it KE at first. That means you must use like a gun and you shoot the proton out. Boom. Then it flies. But it's being repelled. Because the high potential here is being repelled. So it will lose KE. Right? So it's negative change. Right? The calculation of the field strength, okay? That one no problem. But the potential difference is Yes, but no, sorry, because I got a year 3 IP, year 3 ACS IP inquiry. Yes. Yeah. No, because I need to start building up for the next few years, right? SGI IP year 3, ACS IP year 3, MGS IP year 3, please send them all over here. Because by in 4 weeks time, right? In 4 weeks time, right? This entire place is gonna be just ghost town, man. Nobody's, yeah, it's all quiet already after that. Huh? We're gonna talk about damped oscillations. Lightly damped. Wait, hang on, light damping, free or light damping for free oscillations. Okay. I send the amendment, right? What, sorry? Yeah.
Because of the frequency, right? Says here that the oscillation frequency does not change, and that's the frequency for one times two emissions.
Which MCQ is it? This one lah, yeah. Question what lah? 20. So I go back to 20. Is that right? Yeah. Okay, Okay, so hey, this one here I sent out, right? I sent this out in the Telegram chat. Hey, keep the program, eh? I sent it out in the Telegram chat. Yeah. Why you shake your head? No, why you shake your head? I say I sent this out in the Telegram chat. You haven't checked it. Okay. So last year when I was teaching this, right? If you have caught up with the videos for C4, right? I told you that for an undamped oscillation, right? An undamped oscillation, the undamped oscillation will look like this, correct? It look like that, right? Then I said for the lightly damped oscillation, I said that it will follow the same period and the amplitude will start to decrease. So I'll say that, you know, it follows the same period like that. Okay? I say that. Because that's the kind of like the style that I've been teaching so far. This is the like the A-level side of things as well, right? We reckon that the period is the same. But I had to change it because of this question. This question came out, and then I realized that, oh snap, I think I have to, you know, I have to amend what I said, because option D is wrong according to the mark scheme. Option D says the oscillation frequency equals to the undamped oscillation frequency for lightly damped oscillation. So if they say that, then that means it's not the same frequency anymore. You understand this? Right? It's not the same frequency anymore. So, but I know this. I understand it. It's just that we assume the period to be the same. Okay? So in reality, damping will cause the oscillation to kind of like to oscillate a little bit slower, because damping means resistive forces, so therefore it takes a bit longer, right? So you will see a graph that looks like, oh my gosh. Okay, anyway, I show you the picture. Where's my Telegram picture again? I need to show it because the rest of them are like, I don't know whether they get it fully or not. Wait, major amendment, right? Yeah, this one, yeah. So in my Telegram chat, right, I did mention about this. Okay. So the lightly damped one, right, is the red one. You can see that the amplitude getting lesser and lesser. So I draw it this way. So it is a bit longer than the original undamped period, but it doesn't continue to change. Right? It is longer, but it's constantly longer than the original period. You know what I'm saying? So that's why you see, right, the gap here, the gap here, the gap here, and the gap here, they're all the same gap. So they're all deferred by a certain fixed value. Right? But it doesn't continue to get worse. Yeah, that's what I meant. Okay? So because of this question, take it. So this is what we're taking. Can I? Alright. But by right, you should just kind of like usually just approximate it to be the same period. Okay, what's the next question? What's that? 28. 28. Eh, 26 lah. 26. Okay, 26 huh? Okay, who's asking for 26? 26? Okay, good. Right. What's going on here? Is this EMI or is this EM? Is it D3 or is it D4? No. There's a cell here, bro. There's a cell here. Move where? To the right. Okay? The field is pointing out of the page. And therefore the current that's flowing is flowing up. So we understand that the current due to the cell is flowing upwards, and therefore the direction of current is anti-clockwise. What's the equation for the force? What's the equation for the force? Is it raining? Damn. Okay lah, still got about 20 more minutes. I hope it doesn't get you guys, man. Oh, it's raining. It was so dark. It's so dark outside. Okay. Right. What? What? Right, that's the current, right? Okay. So the force, BIL sine 90 or sine 0? Sine 90 or sine 0? $90. But where's the 90? Current is pointing up, right? Field is pointing out of the page. That's the 90. You get this? Right? So current is flowing this way, right? And the field is pointing this way. So the 90 degrees is here. That's perpendicular. It's the maximum force. Okay? This one, everyone okay, right? This one, no issues, right? Okay, hang on. I'm going to ask you a side quest for this question. Right? I'm going to dive in a bit deeper for this. Right? Because I noticed one of the words they used. Right? They use this word here. What? So the question is, why did they use the word initial? Technically, they don't have to put it there. It doesn't matter also. But they did say it there, and which makes me realize that what's going to happen to the force? So this rod will experience a force, right? And this F equals to BIL sine 90, right? But what happens to the force after a while? Huh? Why does it decrease? Huh? Okay. Yeah, but that's not explaining why it decreases. What? Lenz's law? Why is there induced current? Good. So what happens here is that the current that's from the cell is making the rod move. Okay? And from the movement of the rod, it actually induces an EMF on the rod. Right? I mean, if you pull a rod in a magnetic field, does it induce an EMF? It does, right? Okay, I'm going to ask you this. Where's the direction of the induced EMF? Good. Use your right hand rule. Using the right hand rule, so the force is pointing this way. The rod is experiencing a force this way. The field is pointing out the page. And therefore, the induced current is pointing down. So what happens is that the rod is moving and it induces a current that actually backflows, right, against the current that's provided by the cell. What happens to the effective current? Right, the effective current gets less, right? So it's like you have an EMF that points this way, right, and then the induced EMF points the opposite way. This is the concept of self-inductance. Right, the movement of the rod due to the current is inducing an EMF on its own. And this EMF is opposing the original EMF. So the current in this rod is getting less and less. So the force acting on the rod will get less and less and less. So describe the motion of the rod. It doesn't slow down. That's the same as saying slowing down. It's a decreasing acceleration. Try not to say accelerates at a slow rate because then you start thinking that it's slower. So just say accelerating at a decreasing rate or just say decreasing acceleration. Decreasing acceleration. Are we good? Yeah? If that's okay, then we move on, right? So this thing here has a little bit of like has a little bit of like extra stuff at the end here. Okay, what's the next one? What? 28. 28. Let's look at 28. 28. Who's asking for 28? Huh? Who's asking for 28? Again? Second time again? Okay, let me see you're working for 28. Let me see you're working for 28. There isn't any. Why is there no working on 28? Do you not draw the coil at least? Yeah. I want to see that. I want to see that. Draw the coil. Huh? What's that? Oh no. Right. And then it's initially perpendicular to the flux. Like this. Initially it's perpendicular to the flux like that. Yo, you drew that? You draw that? You drew it wrongly. What? I don't know what that is. It's a ring, right? Perpendicular to a vertical magnetic field. Okay? And then when the ring is rotated, so you're gonna flip this thing. Right? You're gonna flip this thing, flip it over, right? And then how does it look like after that? Like this. Right? You know, it looks the same, right? But now the flux is pointing on the back side of the. So it's pointing down to the front side, and now it's pointing on the back side of the ring, right? So now the question is this: if you ask me to find the average induced EMF, then yeah, exactly. So it's 2 times MBA. It's the same thing again and again and again. All right, but okay. No, it's not zero. It's not zero. Because you got to always remember, what's the analogy I always use for this? The ball bouncing, what's the change in velocity of the ball? 2v. 2v. So this one here is MBA final minus MBA initial. Flux is a vector, so direction matters. So if you're pointing on the front side versus you're pointing on the back side, I say back side again. All right, then it becomes just 2 times of MBA over T. We got this? Question, what happens if they say rotate by 90 degrees only? Then it's just NBA minus 0. Then it's half of this. Right? But yeah. Huh? Half of this, not half of MBA. You get what I'm saying? Yeah. So it's MBA minus 0. Okay, if you rotate it by 90 degrees. 29, did anybody ask for 29? Huh? 29? Okay, for 29, I need to show you this thing. Oh, sorry. This is the rectangular coil. Okay? The z-axis is here. The x-axis is here. And the y-axis is here. Okay? Then where's the field? Where's the field pointing? Where's the field pointing at? Direction y. So the field is pointing down. This direction. Okay? So your field is pointing in this direction here like that. Okay, huh? So then they show you that, oh, there's an EMF that's been induced. This is basically 1/4 of a sine wave, or a cosine wave, sorry. 1/4 of a cosine wave. So how should you rotate this thing, right, in order to get induced EMF, basically, right? Starting with maximum first, though. Yeah, starting with maximum. XX, like this, right? Because the field is now passing here, right? So when you cut across like this, you get maximum induced EMF, right? Maximum induced EMF like this. So it's like that. What happens if you try to rotate it ZZ? ZZ will be like this. You know what I'm saying? Ah, skills. Okay. Then the other one is like this. The other one is like this. Okay. So the other one will be rotating like that. Okay. Which will not generate EMF because the field on this side and the field on this side, right, is cancelled off from each other. Hey, what happened? You okay? Don't break my chair, please. I just replaced those chairs. So I'm like collecting data. The chairs there always break because I think that's where all the bigger size ones sit at, right? What? Are you not? How tall are you? 1 point. Yeah, see? Okay. So XX. Oh, so you still have to figure out how many degrees, so how many degrees? 90. 1/4 of a wave. 90 degrees. Okay. Okay. Alright. Anything else? 35, 36, huh? I'm gonna go through 35, 36. 35. 35 is this one? 35. Wow. Say it. N over T. HF over area, but they didn't use F because they said the wavelength, so it's HC over lambda. Right, so I just changed it to HC over lambda, right, over A. So HC over lambda over A. So you double the wavelength, and then you what? Double the photons, you net off. Net off. You go back to the same intensity, right? Yeah. Yeah. Then you double wavelength, right? So it's 2 lambda, isn't it? Like you put a 2 at the bottom here. Yeah. You put 2 here. And then there's a double of photons. 2 here. Cancel off. You get back to the same intensity again. Yeah. That's it. That's it. No, so the formula, but you have to go and remember what does this formula represent? What's N over T? What's H over C over lambda? What's A? Got it? No, got it. Okay, you go to school, right? If you go to school and you're not spending quality time in school doing any of this, right? Then you just start watching the E2 videos.
Well, I've watched all the videos.
When was the last time you watched it?
Last week.
Oh. Why is this not registering your head? Oh my gosh. All right, number 36. 36. Oh boy. Okay. So number 36, just take note of this. Number 36 is the IB's way of announcing to us that specific energy and energy density are back in syllabus. Okay? So we need to remember what specific energy is. Right? Specific energy. They asked for specific energy, right? Oh no, okay. Alright, whoops. So this specific energy, right? And what's energy density? Energy density. What's specific energy? What's energy density? Energy, what is that?
The amount of energy per unit mass.
Energy density? Right, amount no. Amount of energy per unit volume. Density ma. Density is mass per unit volume. So energy density is per unit volume. Specific energy is like specific heat capacity. Right? Energy per unit mass. So this one here is joules per kg. This one here is joules per volume. You got that? Yeah? I mean, specifically, this question is about specific energy. Alright? So we have to find out what's the energy released per unit mass of hydrogen and what's the energy released per unit mass of uranium. Right? So we have... So you see, right? They say convert a mass of this into energy, right? That's the energy release. So 0.024 U over... What's the total mass of the hydrogens that you used? 5U. 5U. All right, and then what's the one at the denominator? 0.48U over 235U. See? 235U. Come on, work it out. Work it out. Faster, faster, work it out. Ain't no time. What's it? See? Hey, why are you looking at a calculator? Okay, see, so 2.35. Okay, anything else? Say what? Are you saying that fusion is more energy giving than uranium? Yes, yes. But one of the biggest problems with fusion is that it produces gamma radiation as the energy. And it's hard to convert gamma radiation into energy, useful energy. So, you know, yeah, but they still want to do fusion. I don't know. Yeah, that's the thing. Anything else? Oi, haven't do yet. Got do or not? Finish already. So what's due next? This weekend, paper 1B, paper 2, time zone 2. Right? Tell yourself that you need to do it. Meanwhile, as you're going through the paper, you would have noticed some of the chapters you're a bit missing one, right? What do? Go and watch the video. Alright, so the bank turns, the bank turn one, please go and catch the bank turn one if you don't know how to do the bank turn. The bank turn is a special thing, right? I did not expect them to ask a question, but it's here again. So you have to notice the bank turn thing. Like this IB people, they are really doing. They will not ask you to calculate, but you need to know the forces. Yeah, you need the concept. Alright, those online, do you have any questions? Jillian, Russell, Ryan, Choi? You're all good? If you're all good, see you guys. Bye-bye. Take care, man. Bye-bye. Thanks, Jillian. Bye.